So this is Jack Jackson. In this section and in this video, we will be investigating inferences for proportions, both confidence intervals and hypothesis testing for two large independent samples. So this is a two-proportion z-test and two-proportion z-interval. We will be using approximation techniques, assuming that these are approximated by normal distributions. And these are good if n times p and n times q are both large for both samples. So the situation we're in is where we have two populations from two independent samples. They don't have to be the same size. The size of the first set is first sample is n1, n sub 1, and n sub 2 is the size of the second one. The statistic we're interested in is the difference in the two proportions of successes in the two samples. That's p1 hat minus p2 hat. So the mean of the sample distribution is the mean of p1 hat minus p2 hat, which is, we know that the mean of a difference is the difference in the mean, so that's the mean of p1 hat minus the mean of p2 hat. And we know that the mean of p1 hat is the population proportion, p1, and the mean of the distribution of sample proportions for p2 is the population proportion, p2. So this says that the mean is unbiased. And you may recall from our earlier work that if you have independent samples, that the standard deviation of a difference is the square root of the sum of the variances. So the variance of the difference is the sum of the variances. So anyway, what we do is we have to find the variance for p1 hat plus the variance for p2 hat, add them up, and then square root. Well, the variance for p1 hat is p1 times q1 divided by n1. Of course, the square root of that term right there would be the standard deviation. Squaring it gets rid of that square root. We're going to add that to the same thing for the second sample, which would be p2 times q2 over n2. So those are the two variances. Add them up and then square root the whole thing, and that gets us the standard deviation of the differences. So there's the mean and standard deviation for the distribution of differences in proportions from two independent samples. Now we're going to use this to come up with the test statistic and a binomial. Instead of a binomial distribution or hypergeometric, we're going to use a normal approximation here. Well, for this to be good, the population size needs to be pretty big. And specifically, the rule I'm going to use is if you take n times p1, that's greater than 30, n1 times q1 is greater than 30, n2 times p2 is greater than 30, and n2 times q2 is greater than 30. Some statisticians use less stringent requirements than that, but this is what I use in my class. Now, the way we're going to do this, we're going to pool our estimate for the population proportion. So under our null hypothesis, we're going to assume that these proportions are the same. And if we do that, then we might as well consider this one big sample of size n1 plus n2, and there are x1 plus x2 successes in that total big sample, if you want to think of it as one big sample. And so that would be our pooled estimate for the population proportion, or our p hat sub p, pooled p hat. Notice this is not the same as just adding the two proportions together. It's not the same as subtracting or multiplying them or even averaging them. It's a different type of calculation. Next, we come up with our test statistic. And our test statistic is basically based on this formula back here for the standard deviation. But here we're going to let the P1Q1 and the P2Q2 both be estimated by the population proportion P that we just pooled estimate that we just came up with. And of course the Q1 is just 1 minus that. And so substituting that in, we get this denominator here becomes basically your standard deviation. And so this is the difference in the means here over that standard deviation. That gives us a z-score. And so that's going to be our z-star test statistic. And if these things are big enough, if the population size is big enough that the NP1, the N1P hat 1, N1 times Q hat 1, and so forth for all four of these numbers for both samples are large enough, then a normal approximation will be pretty good. Notice we are approximating a couple of times here. We're approximating a pooled proportion for the population proportion, and our normal approximation of a binomial or hypergeometric distribution is something we're also doing. Okay, but the good news is this is exactly the formulas. These are the formulas that are used in the TI calculator, say the TI-84 and TI-Nspire, for a built-in 2-proportion z-test, and then a 2-proportion z-interval or uses something similar. So moving on with this, let's try to use this, but we're just going to use the built-in shortcut. So once again, the shortcut is built in. It's nice. You just need to know mainly that this is inferences about proportions and that it is a large sample size. So according to USA Today online, a survey of 1,000 drivers 25 to 34 years old resulted in 270 of them saying that they buckle up when driving, whereas 330 of 1,100 drivers 45 to 64 ages of old indicated that they buckled up when driving. At a 10% significance level, is there enough evidence to suggest that there's a difference in the seatbelt usage of the drivers in these two age groups? Okay, let's use the built-in TI apps to work this out. Note that this is a 2-proportion hypothesis test. The sample sizes are big enough for a normal approximation to be reasonable, and the population size is, of course, very big. So N1 times P hat 1 was 270. That's the number of successes in the sample, and that was greater than 30. The number, excuse me, the number of failures would be N1 times Q hat 1, which is 730. Again, bigger than 30. Of course, the 270 plus the 730 need to add up to the 1,000. The X2, which is N2 times P hat 2, is 330, which is also greater than 30. And the 1100 minus the 330 is the 770. That's the same as N2 times Q hat 2, and that's also greater than 30. So, since those are all big enough, we can use the built-in test. So we just hit Stat on the calculator, go left arrow to Test, scroll down, and you'll see a 2-proportion z-test. So we hit that one and run it. We just enter in the information. X1 is the number of successes in the first sample. In this case, the success is someone who says that they buckle up when they're driving, so that's 270. The sample size for the first one is 1,000. The second sample has 330 successes with a sample size total of 1,100. And we choose not equal to because it just says it's testing there's a difference in, so this makes this a two-tailed test. And we calculate that. And it returns this screen right here, this third one, which is tells us it's a 2-proportion z-test. We're testing the alternative hypothesis that P1 is not equal to P2. The z-star test statistic, using the formula I just showed you on the previous slide, is negative 1.51986, etc. The p-value, which is the most important thing that's going to come out of this, is 0.1285, etc. It also tells you the proportion of successes. So the probability or the proportion of successes in the first sample at least rounds off to 20.27. Actually, it's exactly 0.27. It's 270 divided by 1,000. And 330 divided by 1,100, it turns out to be exactly 0.3. So 30% of the older drivers say that they buckle up, whereas 27% of the younger ones. A pooled p-hat that we did using the formula before, which would be, let me see how we did that. We did 270 plus 330 for the numerator, and for the denominator 1,000 plus 1,100. Do those two additions first, then divide, then you're going to get 0.285. So it's a weighted average of these two. So it'll be somewhere in between these two, but not necessarily halfway in between. And then you scroll on down, you can see the sample sizes as well. So anyway, the main thing out of that is we get a p-value that's pretty large, bigger than the alpha of 0.1. We can also do a z-interval in a similar manner. So we do, again, goes to stat, left arrow to test. This time go down here to B, 2 proportion z-interval. Click on that and enter, or type alpha and then B, and it will come up with this screen right here. And if you've actually just run this one, most of this stuff will transfer over correctly. Now, if we're going to use a 10% significance level, that's our alpha level on the hypothesis test, that should probably be our same alpha for our confidence interval, making our confidence interval a 1 minus alpha, or 1 minus 0.1, or 90% confidence interval. So the confidence level is 0.9. Choose calculate, and it gives us a confidence interval, a 90% confidence interval in this case, for the difference in proportions. Notice that the difference in proportions confidence interval does include 0 there, so that's a good chance that there is not a significant difference. So we're saying we're 90% sure that the proportion of younger drivers minus the proportion of older drivers that say that they use their seat belt is somewhere in this interval here. So it's not very different. Okay. So our conclusion is, with a p-value of 0.129 and an alpha level of 0.1, there's not enough evidence to conclude that there is significant difference in seatbelt usage of the two age groups. Here's another example. Racial profiling is a term used to describe any police action that relies on ethnicity rather than behavior to target suspects engaged in criminal activities. Does, or at least at the time that this was taken, did the Los Angeles Police Department invoke racial profiling in stops and searches of LA drivers? This question was addressed in Chance, spring of 2006. Data on stops and searches of LA drivers from January through June of 2005 for black and white drivers is given in the following table. We have broken into the two races, black and white. We have the number of stops, 61,688 for black, 106,892 for white. That's someone pulled over for a traffic stop. Then of those, then they went and did searches. 12,016 of the black people who were stopped had their cars searched, whereas 5,312 of the white people who were pulled over had their cars searched. Of the people who were searched, the ones that found criminal activity, for blacks it was 5,134, and for whites it was 3,006. So we're going to perform a hypothesis test to determine if there's a greater proportion of searches made for African Americans than for whites. So let's use an alpha of 0.05. Construct a 95% confidence interval for the difference in proportions. Based on our last example, let's see if you can do this on your own using your calculator shortcut. Press pause when you're ready to come back. All right, now you're back. Let's go on and look at the solution. So we run our two proportion test. Well, first I guess we should make sure that that this is even a legit thing to do. We are testing two independent samples. The population size is huge. The sample size is also huge. Over 61,000 for one group and over 100,000 for the other group. Regardless of the p-hats, when we multiply those together, everything is going to be greater than 30. So this is a legit thing to do. So let's go ahead and run that. It's a two proportion z-test on the calculator. We enter this information. We'll take group 1 to be black. So that's the number of successes, meaning in this case a car that was searched, is 12,016, and the sample size is 61,688. For the whites, the number of successes, number of cars searched, is 5,312, for a total sample size of 106,892. And we think that the proportion is higher for blacks than whites, so we're going to do a one-tailed test. And so that's going to be a right-tailed test, so a greater than is here. Choose calculate. It returns a z-value of 94. 94 is ridiculously high from a standard normal distribution. And so it returns a p-value of 0. It's so small, it can't even say 10 to some negative power. It's so small. It's 0 for probably hundreds of digits. So it's extremely strong evidence to say that there is a difference in proportions. In fact, the proportion of blacks that were searched, of the ones that were pulled over who were searched, is over 19%, and it's less than 5% for whites. Okay, a pooled estimate would be about 10% if these are from the same population, which clearly they're not. And we could also do an interval here for the difference. And if you look at this again, I'm using the same information here. So again, this is using the same information. Notice that this input screen here for the two proportion z interval and the two proportion z test is almost identical. On the z test, you have to tell it whether it's two-tailed, left-tailed, or right-tailed. And then on the two proportion z interval, you just have to enter a confidence level. Since we had 5% for our alpha for our hypothesis test, we'll use the same alpha, which leaves a confidence level of 0.95. Calculate this, and this gives you the interval. So the interval of the difference in proportions, we're 95% sure that blacks were pulled over somewhere between 14.1% and 14.8%, 14.9%, somewhere in there. So we're very sure that the blacks were pulled over more often, and we have an estimate of how much more often. Okay, so with the p-value of approximately 0, there's very strong evidence to say that the proportion of black drivers searched is different from the proportion white drivers searched. Actually, we said this was not just different, but more than. So that should say more than the proportion of white drivers, since we did a right-tailed test. The sample proportion of white drivers searched was about 5%. And the sample proportion of black drivers searched was about 19.5%. A 95% confidence interval for the difference in proportions is 0.142 to 0.148. And then, so then we might say, well, wait a minute, maybe it's just that that one group had actually more crime, So let's test that. We have data for testing that too. So let's test that. So, is there a difference in the proportion of searches that result in finding criminal activity between the two groups? So now the sample size is the one searched. That's these two numbers here. And the successes are the ones that actually found the criminal activity. And that's this over here. So let's see if there's a difference there. Again, perform the search or the test yourself now. Press pause. So we're testing for a difference in the proportion of searches that result in finding criminal activity. This time I said difference, so it's a two-tailed test. This time the X is the number of successes for the first group is 5,134 with the sample size of 12,016. The X for the second group is the number of criminal activities found, 3,006. Population or sample size is 5,312. This time I said do a two-tailed test just to say for difference in. So it's a not equal to, and we can calculate that. Again, we get an extremely small test statistic, negative 16.85, and a p-value of on the order of 9.7 times 10 to the negative 64. So it's 0 to 63, decimal places. So this is a p-value is about 10 to the negative 63rd power. That's 62 zeros and then a 1. We round it off. The proportion of successes in the for blacks was about 42.7%, and for whites was about 56.6%. So what does it say? It says, well, blacks were less likely to be having the criminal activity given that they were, if they were pulled over, out of the ones that were pulled over. The proportion, the confidence interval, 95%. Confidence interval, again, since we're using alphas, 0.05 throughout. This is the same information here, just a little to proportion Z interval this time. And all these numbers will have already been there if you just ran the Z test. You just got to put in the right confidence level, 0.95, calculate, and it comes up with that. Once again, it retells us the two sample proportions and the two sample sizes, and it gives us the confidence interval. It's negative here because the first group is less than the second. Okay, and so it's saying that the African American or black group was less than the less likely to have finding criminal activity if they were pulled over. So when we combine this with our previous result, there's very, very, very clear, strong evidence that unjustified racial profiling was occurring in this police department at this particular time. This was a few years ago. We can only hope that they have improved in the meantime.